All right, we should be live. I'm going to go check the. I got a lot of
Sean was
words.
calling you out for being 30 seconds late, Jesse.
It was. That wasn't my fault. It was soundly. We were in a deep conversation. Well, good evening, everyone. Thanks for showing up. I've got something exciting to show you. At least I think it's exciting, and it's been sitting around for a year, and it was time to pull it out when I saw some of the flack Soundly's been taking.
Almost a year. It's been about 10 months.
Yeah, that's true. So yeah, coming up on December, we'll say. So it's not quite a year, but this data has been just sitting, and it was data I collected back then, and always wanted to do something with it because I knew what it would show us, and but now it's time to do something with it. So that's what I'm going to show tonight. There's going to be a need to kind of do a little education on what it is too, because it's not something familiar to most people. It involves GPS. I think we're allowed to use GPS now, right? Didn't Bilu say it was okay? I don't know. I see flat earthers using GPS, so I'm going to use GPS. I use GPS all the time. So I'm going to talk about what it is that I'm going to be showing in terms of the coordinates. It's actually a coordinate system. I've got a lot of windows open, so let me share my screen and get this started. All right, let's see here. What do I want to show you first? I guess I'll show you what I literally. No, you know what I'm going to do before I start the GPS part? I'm going to talk about what brings us to tonight. Let's do that. And this is a slide presentation I had been preparing for another video. And I haven't finished it yet, so this is kind of rough, but it'll be a good lead in to what I'll be demonstrating later using the GPS data. How's that? So I called this Earth curvature plainly visible and easily measured. That's pretty much my contribution to this whole it's not even a debate, but this topic, let's say. And so I'll go through this.
I think the correct word is debacle.
Okay. Yeah, especially when, as you'll see in this little presentation, they keep reciting the same wrong thing. And so why doesn't this go? Oh, here we go. So for flat Earth believers, still searching for the clown frown in 2018. Some people might recognize this photo I took. It's about a year ago. That's in 2016, actually. And that's what I call the clown frown. People think that's what the curve should look like. And of course, it looks nothing like that. Still searching for the clown frown? You're not going to see that. I think that's hilarious. Yeah. You will never see the curve searching for the clown frown. So I've made a lot of videos about the curvature of the Earth and how easy it is to see it. Especially these two, flat Earth curvature confusion. I go through that in depth. It doesn't seem to do any good, though. The people are still quoting 8 inches times the mile squared and using it incorrectly. I go into great detail in both of these videos about what it should look like. And in this little presentation, I'm going to try a little different twist on it, as you'll see. You can also check on my channel for, I wouldn't call this surveying because, surveyors don't generally hold smartphones up to their instruments to take pictures, but I do this for people to see what I see when I look through my telescope. And so there's a bunch of videos like that on my channel. I'm not even going to read this. It was basically an idea of what I was trying to accomplish in this presentation. And like I said, I want to kind of go through this a little quickly just to give a background to what's happening later in the presentation. So, let me back up. So basically, this is one of these Earth curvature charts you'll find out on the internet. This one happened to be prepared by Brian Mullen and some other people I don't know there. And they are always calculating the drop. And everyone quotes these charts, and then they misapply it, saying that's the missing curvature. What they fail to do is establish that line right there. There's only one way to do that, and that is using a surveying instrument, or taking clear bottles, filling it with red liquid, and suspending them to create that horizon, or that horizontal plane. Lately, I've been pretty much focused on talking about this aspect that no one is talking about, and that is the theta, the angle, okay, that is easily measured. And so what I've added to this chart is I've gone ahead and calculated this for people, this little table I'm throwing in here now using nautical miles. You can use this to get an estimation of the amount of arc across that distance. So moving on.
Wait, so you're saying that 1 minute and what's that, 0.10 arc seconds?
You could just say 1 nautical mile is going to be 1 arc sec, or 1 minute.
Gotcha.
Yeah.
Okay.
Yeah. And I'm showing people here what I use to calculate that, and that's on a sphere. You could see here it actually talks about the spherical Earth or the ellipsoidal Earth. You're going to see small differences as you go further and further. But that's a nice calculator right there, made by some guy named Stephen Morse. I'm throwing these calculators up here to just let people know that these exist, and that surveyor's drop. This 8 inches times the mile squared, I've been asking people lately, well, where did you hear about that? They don't realize where that even comes from. Mark Sargent says it comes from mainstream science. It's a surveying formula. And you can calculate it with or without refraction involved. Flat earthers like to bring up refraction all the time, but they ought not. If they want to believe the Earth is flat, refraction works against them. It kind of flattens out the curve. So it's the obscured thing that they keep confusing with the drop. And this is from the Metabunk. 8 inches times the mile squared is going to calculate that drop. From what? From the horizon, from the horizontal tangent plane. That's a whole different calculation there, that hidden amount. It's different. Now, this comes out of that presentation called, or the video I made, Confusion About, this one, Confusion About Curvature. I forget the title, actually. But this is the important thing here, is establishing that horizontal plane. And that's what's shown in a lot of the photographs that I take. So there's your 8 inches times the mile squared. And that's what it looks like on a curved Earth. The horizontal tangent plane is going to be perpendicular to the vertical plumb line. That's the drop, 8 inches times the mile squared. Of course, there's always going to be visible objects out there. And there must be thousands of these flat Earth videos talking about, I shouldn't be able to see that. Why not? You can see it. It's there. And this is their confusion, using 8 inches times the mile squared, which, like, for instance, looking across Lake Michigan from the, Warren State Park, the Sears Tower is below the horizontal extended. If people don't know that, I do have a picture of it a little bit later in this. The Sears Tower is below the horizontal tangent plane. So stop confusing your visual line of sight with the horizontal tangent plane. All right. And then I go into the fact that people are expressing these things way beyond the attainable precision. So use this one to calculate the drop below the horizon. Use this for the tangent plane, for the 8 inches times the mile squared. Don't mix them up. Let me move this. Okay. I made this a long time ago when, I don't know, I haven't heard anything about Dr. Zach anymore. So I thought, you know, he's very good in AutoCAD. Maybe he would pick up the banner and help people understand this. So here's a table using that 8 inches times the mile squared. It comes from a really old book, and you can get even older books that tabulate this. And so what does that mean? It isn't something someone invented. It's actually measured. You can literally measure it and model it. So really, you consider this table of values like an old way of modeling something that is easily measured. And the 0.57 is with refraction considered. So think about it. 8 inches is 0.67 feet. So 8 inches times the mile squared, it's 0.67 feet. It's a tenth less when you consider refraction. So it lessens it, you know. And there's the example just using 10 miles. And there's a longer one, 47 miles. So if people with P900s, if they could establish the horizontal plane, they would be able to see these distances. For instance, there's this lighthouse. The horizontal crosshair is almost 12 feet, but the lighthouse is nearly 60 feet high. So here's the other thing I wanted to get across to people is that these charts go out to what is it, like 3,000 miles? I mean, who can see that far? You can't. You know, you're lucky to see, 50 miles, 60 miles. Some places you might see up to 100 and some miles, or even further. But what's it take? Well, it takes elevation. You got to be up on a mountain or something.
Jesse.
Yeah.
Do you want me to let you know when people have questions, or you want to hold them to the end, or what?
Let's hold them to the end. And honestly, I want to cruise through this a little quicker. I don't want to take a lot of time with this. This is going to be another video, actually. But again, here I'm showing people this arc. Here's the other thing. People talk about the tilt. Why can't I see it tilting? You can't see 10 minutes. In 10 miles, it's 10 minutes, 10 arc minutes. You can't see the 10 minutes tilting away from you, but you can measure it. And that's what I'm going to show with the Lake Pontchartrain Causeway in just a little bit. So this is the thing. This is my twist. I'm going to try to help people try to visualize what's going on here. Let me back that up. I'm kind of proud of this. So we're going to take this chart and we're going to turn it in our hands and twist it so that we're looking that way. Okay. So now we're looking that way. Get it? So let's see. Let's zoom in on this. This thing needs some work. Sorry. It's being debuted right now. So let's zoom into this little area. Okay. Get a little close up here. So we're looking that way, and that means you're looking that way, out. Okay. And the drop of the curve is right there. Okay. And of course, they ask to see the curve. You show them the curve, and what do they say? Well, that's due to anything but curvature. It's perspective, it's atmospheric, baloney, it's whatever, but it's not the drop of the curve. But come on, that's what this is. And I can show this to you in like 1,000 feet. So
That's
so
actually a really good graphic. I like that.
okay.
You should polish that one up right there.
Okay. Yeah, it needs, I got a little too many clicks in here to get it there. So this is just my folder filled with the different tests and things that I've done, the different measurements I've done. And I did the first one I did was in 2015 in November. And it was the 1 mile test. And I wanted to measure that theta angle. So in just 1 mile, I went to these 2 mileposts on a north-south highway, Route 206, and I made a video about it. It's up there, and I measured approximately a minute, 11 seconds, taking numerous repetitions of angles there. So I went back there. I don't think I have it in this here, but I went back there a year later and did something a little. I added some complexity to it. I set the instrument and target up to be level with each other. So even though there's a small grade change across, across that mile, I set them up level with each other and did the same thing and pretty much came up with the same result. The next thing I did was to go up onto this Apple Pie Hill tower and take that photograph using my auto level. And that was as a result of watching that video called Flat Earth Proof 3 Land Ho, which uses this, this picture of Philadelphia from Apple Pie Hill saying there's 335 feet of missing curvature. And so I went up there and measured zenith angles with my T2 to the top of what I didn't even know which building it was at the time, but I measured those angles and couldn't do reciprocal zenith angles, right? So I've got these measurements from the tower, but I could not go on the roof of the Comcast building to measure back. So I did the next best thing. I went down to the Camden waterfront and triangulated the top of that Comcast building, similarly to the way we did the Marriott Hotel at Lake Pontchartrain, located and determined the elevation of the top of the building and its coordinates, the horizontal position. Oops. So you can see what the building looks like through the telescope. Triangulated it and did perform the intersection computations to position those corners. There it is in 3D looking at it. Little sketch. So there's the building. There's the little the corners that I measured. So now with that information, I could determine the relationship between the two locations. There it is in Google Earth. So just flying through this here, we do have curvature. It's not missing. It happens to be 28 minutes and 5 seconds. Again, you're not going to see that. You're not going to look out there and see 28 minutes of tilt in a building. It's just not, it's not possible. So I started making this sketch back then to try to get this point across, and maybe I need to do something different, but that's what it is. I think the rest of this is, okay. So here, I'm just summarizing that. In 32.4 miles, I had 28 minutes and 5 seconds. So if we look on that chart, in the chart that I made, you'll see it corresponds to that. I'll probably drop off from this now. I'm not going to continue. This is okay. Here's the picture taken using the auto level. So no angles measured. Just take this up, level it up, look out across, take that picture. So that's what the Earth's curvature looks like. You're not going to see curvature across the field of view. You're going to see it dropping away from you out to whatever you're looking at. So it's not going to look that way, right?
Correct.
You can't see the curve.
They are clowns. There's no doubt about that.
It's so sad.
They're looking for their own frowns.
And I think I'll bail out of this now. I think I got the point across. The rest of it goes through what else is in there? Some of the shorter tests, which I do plan to make another video of those. The 200-foot test, 500 feet. I just did. What am I trying to do here? I'm going to close this. I just show this last one here. Well, this is good. I'll show you this. Show you the Cape May Lighthouse. Let's look at that. Good. So I'm on the Delaware shore, looking across the Delaware Bay. Here's the nautical chart. Oh, by the way, I commented soundly in your video, your last hangout. Thrive and Survive is showing nautical chart of Lake Pontchartrain.
Yeah.
Where did he get that? That's in my video. So,
yeah.
You know, here he is using a planimetric display of latitude and longitude, which is arc measurement. All right. You know, that's
he's using an extremely detailed map that was created by people that created it knowing that the Earth is a globe.
That's correct. And it's plotted at, the plotting is 1 arc minute per mile, per nautical mile. So, so here is, oh, let me click this. Yeah, so here's Cape May. There's the Cape May Lighthouse. And this is the location where I made this measurement at, I think that was called Broadkills Beach. And there it is. That is the Cape May Lighthouse. And it's just, you know, it's hilarious to me. Oh, and there's even water towers over on the right. You see these water towers. So, okay, yeah, they are right. Let me back up. That's these water towers here. There's a tank. And these are probably what you're seeing in that photograph here. This, I'm trying to remember the height of this. I think it's like 157 feet high. And this crosshair is at elevation 12 or something. I forget what I have it at. Obviously, it's not at 150 feet. Yeah, here's these two water tanks and a water tower. And, okay, this is what 1 mile looks like. That's 1 mile of curve. 1 mile, 8 inches times the mile squared. There's your 8 inches. There it is looking back. Oh, and this is
wait. So those were two different stations set up.
Looking, yeah. This
what
is.
do you call it? What's the word you call it?
Well, this tripod.
They're established, or there's actually.
Oh, the station. Yeah, this one is at. This is at mile 27. This is on that Route 206.
And they're both set on horizontal, and they're both looking over the top of each other.
Correct.
Nice.
So yeah, this is the test where I set them to be level with each other. And that's the theodolite looking at that target. And that's the theodolite looking back up at milepost 28. And I did this over water too. I did the same thing over 2 lakes, setting the tripod for the target and the instrument the exact same height above the water. And you get the same effect.
Yeah. Pretty obvious.
And here it is. This is a picture not taken by me. It's by someone who's on YouTube as Red Pill World. And he made a series of videos, and he's measuring a zenith angle of 90.0007, and that is, in other words, 7 seconds down from the horizontal to the top of the Sears Tower.
Wow.
That means if he puts the scope back up 7 arc seconds up to be at 90, the building is entirely below the horizontal. I forget what his elevation is there, but it's like 200 feet or something. I mean, it's not.
Yeah.
What's the Sears Tower, about 1,400 feet tall or something?
Don't know.
So that's how it works. Now, and here's the short test. I'm going to probably bail out of this now. So here's this little park I have. These distances are hundreds of feet, and I have reciprocal zenith angles measured. I've done this a number of times. I just did it on this triangle right here, setting the instruments and the targets level with each other. That's just another interesting facet to do, another interesting aspect. And I did that, a week ago. So that data is in the can, ready for another video. But the point I'm making here is that the differences correspond to the differences in latitude and longitude. And I pulled these right out of Google Earth. And, when you take your mouse and move it across Google Earth, you can look in the lower right. These numbers are changing. And if you can find, say, a north-south highway and find mile markers, you're going to notice that it's going to be about 1 minute of arc in about a mile, roughly a mile. I mean, a nautical mile's slightly longer than a statute mile, but you can see that, and that's measurable. You can actually see it and measure it. That's it. Let me get out of that. So here's the Lake Pontchartrain Causeway survey. And next I'll show you what I was going to show you before. And that is, where is that video? Oh, come on. I had this all queued up. Give me a second. Not that, not that. Can't believe I don't see it. Shit. Well, I'm going to go find it. Bear with me. Let's see, is it down here? What do we got? Nope. It's worth the wait.
I believe it.
This one? Nope. I'll probably go through all this and then find it. Nope. It's a little bit later. Nope. We should have a hangout sometime and go through Little Tinsis Bayou. Is it here? Nope.
That was a good wide angle shot of 3 Lakeway, though.
I can't believe I must have these upside down. Sorry, folks. I think it's this set here. Nope. Crap.
It's all right. Take your time.
Lake Pontchartrain, 1210. It's got to be in here.
What you hunting for?
It's the movie of the GPS receiver on the vehicle driving across Lake Pontchartrain.
You did that early in the day. It would have been one of the earlier shots, huh? It would have been in the morning, right?
Well, we did the
Or early afternoon.
triangulation. See, that's later.
That's later, yeah.
It's got to be after this. It's got to be after that one.
It's when we went from this side to the other side to the night shots.
Well, this one's the triangulation.
I thought you did it before I even came out there. I thought you ended up meeting me over on the North Shore, didn't you? At first.
Oh, you think it was earlier?
Yeah.
Nope. That's me adjusting the instrument. This is ridiculous. Nope.
Just go through them sequentially. From the early.
Oh, here we go.
There we go.
This is it.
Yeah, see, early in the morning, 7 o'clock. Yeah.
I don't know if you can hear that. So I've set it at fixed time every 15 seconds. So
it takes a GPS reading every 15 seconds?
Yeah, so the next time we do this...
Oh my God, I want that mount right there.
Next time we do it, it's going to be, I'll just do it 1 per second and get a good saturation.
Yeah, if that shot right there you're looking at in New Orleans,
yeah.
I want your mount with a camera on it that watches New Orleans sink under the horizon as you drive across.
So I called these points Lake Pontchartrain northbound, and then they just incremented 30, 31, 32. So that's just, I hope that was worth the...
So you're recording a GPS location every 15 seconds as you cross the causeway.
Yep. And here's what that ended up looking like. And you can see the elevation is, I have 19. I don't know what the elevation is supposed to be of that bridge, but I ended up with 19. 19.1. That's a tenth of a foot. Now here, I think I either have bad shots, or I think I'm going over one of the humps.
Over a hump, yeah.
There's 56.5, back to 38.9, and then back to 19. Are there
consistently 19? That's amazing.
Yeah. Now these two, I don't know what happened there. 21. I'm not sure what happened.
Well, there's the marine span and the bascule that are both really tall. That's probably that 56, the 56 footer.
Okay.
And then there's a marine hump, which is pretty short.
Okay. So well, maybe 2 shots got snagged on that section. And then we're back to 19 again. And I have this over in Google Earth. Sorry for all the screen changes here. Here we go. And so, come on now.
What are those numbers, Jesse? Is that inches or something?
Just they're just the shot numbers.
Oh, shot numbers.
Yeah. So here's probably one that's up a little bit. No, that's not up.
They're right there. It should be up.
Yeah, 56.
There you go. Yep. That's the let's zoom out a little bit. I'll tell you which one that is.
That's right there. That's right in the middle, pretty much.
Yeah, that's probably the marine span at 8 miles. That's what it looks like.
Okay. Oh, Okay, I've got the mile markers embedded in my descriptors. Let's take a look at that. Which actually brings us to the next phase of this to talk about, and that is the file that I output. That's this. So these are the point numbers in column A, and these are what are called Earth-centered, Earth-fixed coordinates. And that's what I'm going to talk about next. And then each one I have a descriptor is the milepost and what the elevation is on the road. So this is something that people are not really accustomed to think. They don't realize GPS actually works in this system right here. It does not work in latitude and longitude. It works in ECEF coordinates. These are converted to latitude, longitude, and ellipsoid height. This information is embedded in the Rhinex file, which is what this. Tell you what, what I'm going to do is close things as I'm done with them. Yes, done with that. I'm done with Google Earth, and I'm done with this.
That's actually an interesting point. The ECEF.
Yes.
So expand on that.
Yeah, that's what I want to talk about next. And I want to show what the file looks like. So here's a Rhinex file. It's just a lot of numbers, right? But I have a video that I'm going to show you a glimpse of where I go into detail on what is contained in this file. And it has ECF coordinates. There's the ECF.
Are those are the raw readings off the sensor?
Yes. What it does is it actually computes the ranges from the satellites to the antenna. And I've made this point to a lot, all the time, that if people really want to believe that these are coming from ground-based cellular antennas, these distances are 20,000 kilometers, like 12,000 miles, and right. they're all pointing to space. It's just dumb. So here's a video I made here. GPS antennas mounted on buildings, proof. So I'm not going to show the whole video, but I am going to tell you that if you want to doubt the GPS or its effectiveness or that it can work, every road these days, all roads are being built with GPS mounted on the dozers. It's GPS is mounted on agricultural equipment. You name it. It's being used in a lot of ways. So whether it's on cell towers or not, it works very well. And that's my lead in to what I'm going to show next, the results of that survey. Okay. So ECEF is, these coordinates are in a system that really does not even require an ellipsoid. The only reason we're showing the ellipsoid here is to show you how these ECEF coordinates are converted into latitude, longitude. But the z-axis is the mean rotational axis of the Earth. So the z coordinates are positive coming up from the plane of the equator. The x-axis comes out at the 0 meridian in Greenwich, and the y-axis is at 90 degrees to it. So over in New Orleans, we have positive z coordinates, and we have negative x and negative y. So that's how ECEF works. So it's not elevation based or anything like that, but from point to point, you can get the actual shape of something, and that's where we're going. It's all about the clown frown in this video. So let's look at that next. I had invited Chris to come on tonight to talk about his work. I gave him these coordinates, and he did incredible work in AutoCAD, which I don't have an AutoCAD license on this machine. Even if I did, I can't do what he does. I'm not an AutoCAD guru like he is. But he was able to take those XYZ values and display them in such a way that he could replicate what it would be like to set up a theodolite. If we could get permission to set up a theodolite at about midway across the causeway, and then look either way, okay, that's what he's done here. So at this midpoint at point 766, which is about milepost 12.3, that's a GPS shot. And here what we're doing is saying at that GPS shot, we're going to create a tangent line, just like we would do with theodolite or an auto level, and construct a model where we strike out that tangent in either direction. And you'll start to see it deviate or separate. By the time you get to milepost 23.5, we have a change, a drop, let's call it a drop of 23.5 feet from the tangent line to the concrete road surface. Okay, and then just going on, he didn't label every one of these. Let's go to the next sheet. Which sheet is it? Okay, this is the other end. This is up. This is at the beginning at milepost 0.26. It's my point 721. It's elevation 19, but the concrete roadway is 96.4 feet below the tangent.
Nice.
That tangent is striking out. Is that tangent, or like I should say this line is tangent at that mid shot at point 766. All right. So we got 96.4 feet on the south end. This is the south end of the roadway. And let's go up to the north end. And that's at milepost 23.62. Same elevation. All right. These are level. Okay. But it's 82.2 feet of a drop from that tangent plane.
Yeah. Who would have thought that?
I always knew it. I wanted to somehow display it, and I don't have the AutoCAD skills to do it. But Chris did a great job. He was going to be on tonight, but he had something else that he had to go do, so he couldn't join us. But I'd like to get him on another time. He does some amazing work in AutoCAD. He draws the equinox, he draws the sun, he draws the solar system. And, he's a survey CAD drafter. He does a lot of survey plans, but just with the side hobby, he likes to draw all of these other three-dimensional depictions of what's observable. So here's the thing I'll say about this presentation, these graphics. Again, you cannot go and see the clown frown. You can't see it, but you can measure it. It is not something you're going to see. In 26 miles across that causeway, think about it. Where would you have to be, even if you were on one of the shores looking at the causeway straight on, with north to your left, south to your right, you're not going to see this. You cannot see it. It's not able to be seen. But I don't think you can see the causeway from over there on those railroad tracks.
No, you can't see it over there.
Right, but maybe if you took your drone and hiked it up, you might catch a glimpse of the causeway, right?
Yeah. So interesting thing. Whenever I went to Manchac recently and to film the transmission lines from the other side, I turned around and I could see New Orleans, but in between me and New Orleans is the causeway, which was under the horizon.
Okay, right.
So it's like, you can't see it.
Oh man, we did go. I wanted to stay about an hour. We're about 15 minutes over. I apologize for some of the diversions. Hopefully, it was a good lead up to this. And to me, this is what I've always you know figured it would look like. And by the way, this does prove out the 8 inches times the mile squared. If you calculate these mileages, you're within several feet of both of these drops, which is pretty cool.
Mm-hmm.
Um, last thing I'll show you is what I did this week, and this is just 2 video clips I'll play.
And
Of
let me just make this point too, Jesse.
Yeah, sure.
Those tangent lines that you're showing and how high they are above the causeway.
Right,
If you were out like 90 degrees from the causeway
right.
and you were actually looking towards the causeway, those drops would put the causeway behind the horizon.
Yeah.
So even though you could see the causeway directly in front of you, as it moved away from you, it would drop behind the horizon. And that's the thing that that flat earthers don't understand. The horizon is actually, horizon is not a straight line left to right.
Oh, that's a great point. I'm glad you said that. You're right. So you might see, even if you could get to a place where you could see, like, say, the middle of it,
Mm-hmm.
but it's going to drop off because of the horizon is a curved.
Right.
It is curved.
Right.
Yeah, it's good. This is from a place in Connecticut on the Long Island Sound. It's called Sasko Beach, or actually, I was on what is it called? South Pine Creek Beach, and this one is going to be One World Trade Center. And again, I don't have all the details, like the mileage and everything. I can't tell you right now, but actually, no, I can. I've got it in my field book. The distance from where I am to this, what I'm about to show you. Okay. This is 48 miles. Unfortunately, you can't hear the birds chirping and the nice wave action of the Long Island Sound. So, my telescope crosshair is at elevation 18. It's hitting the top of the One World Trade.
Yeah. So that's a horizontal line that starts at 18 feet.
Correct.
From your location, that is hitting the top of the One World Trade Center.
That's right. And this day was quite hazy. There's definitely miraging you could see on the bottom, but it has no effect on what we're looking at here.
Right.
And here it is through the T2, which has much better optics than that other electronic instrument, the S7. This is not an easy thing to do, to put the phone up to the telescope.
We got to find a way to mount that thing.
I know. There's some advantages to this, though, because as you move this, you can see you get darker. Like if I put this in a video player and just tweak it step by step, I can get some good snapshots.
Right.
So that was One World Trade. Here's the Empire State Building. And I did this over and over for a couple hours to just make sure I got, as the conditions were changing from like 9 o'clock till noontime. Now here, I'm looking at the Empire State Building. It's 45 miles away. Just want to make sure everyone sees it's 90 degrees. Horizontal, that is. See that mirage? Oh yeah, see the mirage here?
Yeah.
Right there?
Uh-huh.
You catch that all the time. This was my first time seeing miraging like this, in person. It was pretty
Right.
cool. I'd really never really looked for that or paid attention to it before.
Well, I mean, it takes up such a small field of view that you can't ever see unless you have zoom camera on it. Some type of magnification. I say zoom magnification.
I've got, like I said, about 6 or so sets of this, and some are better than others. Depends on what was going on with the sun and the haze.
There's only been one ever time that I've seen like long distance atmospheric effects with my eyes, and it was looming on the causeway one time, and I could see it, with my eyes. I could see it looming.
You could see it.
Yeah, but it's so rare to see something that drastic, that you hardly ever get it. You have to look for specific conditions,
Right.
for it to happen.
I've seen that you were actually on railroad tracks and filming cars going across, and they're like, it looks like they're flying up in the air and stuff.
Yeah, those railroad tracks are pretty awesome study. I really like that study, and nobody really talks about it. Nobody even cares about those observations, but to me, it's a very important observation because it shows you that the mirage itself isn't affecting the position of the cars. Even though the mirage is there, the cars are still where they're supposed to be.
Well, that's an interesting point too. And in terms of measurement, survey measurement, this is one of the things that gets thrown up often to say, oh, what you're seeing there is flawed because of atmospheric distortion and all of that. The point to that is that we don't make observations through those conditions.
Yeah.
Let's face it. You could go out and do some survey work, and on one day you can see really far, a mile or more, right? And you'll say, okay, we can measure these angles. On another day, the thing is so fuzzy and so messed up, you can't really point to it. You're gonna shorten up your distances. You're gonna go at like 500. You're gonna cut it in half, and see if you can make some decent measurements that way. And that's, by the way, that's back in the day before GPS, where we definitely relied on theodolite observations to measure angles. Nowadays, really, we use GPS as much as we possibly can, and then supplement it with total station measurements that are basically maybe 500 feet, 1,000 feet. That's about it. It's all short lines, and atmospheric conditions don't even play into it, which is why I bothered to spend the time doing the short tests, 200 feet, 500 feet, 1,000 feet, where it's not affected by any distortion in the atmosphere. You can clearly see the target. There it is, but yet you can still measure the tilt of those plumb lines. So,
right. That's something I'm looking forward to with Little Tenses Bayou. I want to see you do that.
Well, yeah, that was the one thing we didn't get to. We did a lot of work with the lanterns, and I still think there's some presentation we can make out of that. And of course, George has still, not delivered on the photographs we need to finish off Rainy Lake. Rainy Lake should really be a presentation, a video. It's fantastic work. I mean,
right.
You don't.
He did a lot of work. He definitely needs to do a presentation on it.
Oh yeah. I mean, come on. That guy stood up. He stood up all those poles, climbed those trees. He just did an immense amount of work. I really love that entire test he did, cutting the targets to be. He used perspective to create targets that all appear the same size at the various distances. That is so. It's innovative. It's very cool.
Yep.
And then you have both tests. You've got the tangent test and you've got the Bedford level test, all in one laboratory, or you could say. And you're out on water. We're walking on frozen water, which is curved.
Exactly.
Which I do have the XYZ positions of all of that as well. We can actually show the tilts. We can show all those relationships. I keep bugging him. Hey man, when are you going to give us those pictures? And Walter Bislin has offered to model the whole thing, which who saw that coming? That is very cool.
Yeah, that would be awesome.
Yeah. So,
Walter does some good work too, man. I can't even imagine how many hours he's put in.
oh man, his blog is really good. So
Absolutely.
I'm honored to actually have that Philadelphia thing in there. He felt that was worth putting in there. He's got your stuff in there. Pretty cool. So I think that's it for what I wanted to present. I don't know if I guess I should go look over. Do you have anything in the chat that people are asking?
I tried to keep an
early
eye on it. It started with a couple questions. One question and a comment, but then it kind of devolved into a flat Earth debate as normal.
Yeah.
But Rob, I guess his name is Gayet or Gayat.
Oh yeah, Rob. Yeah, he comments. He's in my Facebook group.
Yeah, I know Rob, but I don't know how to say his last name.
Okay. Yeah.
He says, "Hi Jesse, is there a range of values for refraction, or is it a pretty well fixed value?"
All right. The answer to that is, if you look at what is generally used, it's 0.13 or 0.14. That is what is selectable in the most data collectors, surveying data collectors, where you can apply refraction or not.
Mm-hmm.
And it's fixed there, but it's recognized that it's, that's for under nominal, what do they call it? Normal conditions.
Right.
And again, it's really being applied to very, very short distances. So long gone are the days of measuring 10, 20, 90 miles. That's not happening anymore.
That's not needed because of GPS, right?
Correct.
Yeah.
So yeah.
So let me ask you along those lines. Let me kind of go into that. What have you personally witnessed as far as refraction goes, and also like when you say a number like 0.13, what does that number actually mean?
I think that is what is being applied to correct the zenith angle, and it has more to do with the EDM, the distance measurement. Okay, so the fact is that the path of that EDM, that light beam, is traveling a curved path, so it's there to correct that. But again, it's because of the short distances. We're not measuring 10 miles. It's not. There's not much of an effect there.
So you've obviously taken a bunch of long distance measurements just as part of your interest in your hobby, but it's not a typical thing that you would do during your workday. That's what you're saying.
Well, any of the long distance stuff that I've done is mostly pictures through my telescope showing that drop of the curve. I have done some triangulation just to kind of replicate like the angles between lighthouses, and I find that I can the measurements I'm making today are what they made long ago to establish those positions of the lighthouses. I mean, a lighthouse is a critical beacon. It's a navigation beacon. People need to know where it is on that nautical chart. How did it get on the chart? Geodetic triangulation. So I can take those positions, put them in my software, or even just write them in my book if I'm using my old T2. I can cite one lighthouse, compute the angles to the others, and literally turn to it and find it. There it is. So most of the long distance stuff I've done has been all angular.
Yeah.
And I think surveyors out west, out in the plains and places like that, and again, this is pre-GPS days, they definitely measured very long lines. They could. Over here in the East Coast in New Jersey, Pennsylvania, you got a lot of hills and valleys, and it's hard to find a place where you could literally measure many miles. So I've measured I guess for me, the longest EDM distance I've measured has been just about something like over a mile, and that was in the 80s. So
Yeah.
it's just not something that's needed to be done. You don't have to do it.
Okay, so the next comment was from Larry Scott. And
Oh, Larry, yeah,
he said Jesse needs to go to Shenandoah Valley.
I'm going to meet with him. He's Larry. Go ahead, finish what he said there.
He just finished that with real triangulation.
Yeah, he's he's an interesting guy. He's got a lot of experience, and I look forward to meeting with him. But right now, he's like, I don't know, he's like down in the Caribbean. I don't know what he's doing down there, but no, he's on a long trip doing some survey work in the Caribbean. But maybe in November, I'll get to meet up with him, and we've exchanged a lot of emails. He does a lot of what he calls recreational surveying, and that's a good term for it. And he's got this valley where he can do pretty good long distance observations to a tower, I think, a radio tower. But what he's inviting me to do is join up with him, and we'll do some reciprocal zenith angle measurements. I think he's talking about like over a 20-mile valley. And the other thing he does a lot of is astronomic azimuth observations, which I used to do back in the 80s. And last one I did was in like 2001. Again, not something we need to do anymore because we can get an azimuth from GPS very quickly, and it's quite good. When GPS first kind of came around and surveyors started getting GPS equipment, there was a big question, hey, how do the azimuths work? And I was involved in some early testing here in New Jersey where we had some pretty long lines established by GPS. We did solar azimuth observations and Polaris. We waited till dusk and observed Polaris and compared all of those azimuth observations, and they were within a 1 arc second. So we were happy with that. But yeah, I want to get with Larry. It would be fun, and no doubt maybe some videos will come out of that trip.
Paul J in the chat right now ask Jesse if he access to a gyro compass as well.
Well, that came up today at work, and gyros. He says gyro compass. There's something called a gyrotheodolite. Is used a lot in tunneling, basically subterranean, in mining applications and
Gotcha.
Constructing tunnels for trains and highways and whatever. Because when you start traversing linearly for miles, you're going to start to have some drift, and without any ability to check into other control points laterally to control that drift, you will start to drift off course. Gyrotheodolites are very interesting instruments. I've not used one myself. I've looked at the information about them, read about them, and I know people who have hired people to do it. It's a very specialized thing. They're very expensive. That's for one thing. They're an amazingly expensive piece of equipment. Very sensitive. You got to really know what you're doing. And I'm hoping to learn how to use one. I think I'd really like to maybe venture off and learn how to get involved in using a gyrotheodolite for some of the tunnel work we get involved in. And but again, think about that. That instrument is working in conjunction with the rotation of the Earth, and they work really well. And that's another flatter thing. Like, you don't see that come up like, hey, by the way, how did they they do the channel? You know what I mean? The tunnel that goes from Great Britain to the Europe, under the English Channel. Well, they used a gyrotheodolite, on that, and that instrument's used all the time in these subterranean conditions where you've got to control the direction, and that's how they do it.
So Paul then follows up with, soundly, I think they are perfect proof for rotation.
They are.
So they actually demonstrate the rotation, gyro theodolites?
Yes. I wish I could speak more to it. If Larry's still on, Larry will know. If he's still paying attention, he'll maybe pop a link in.
I've heard that the only gyroscopes that are that sensitive is the ring laser gyros.
I have to tell you, it's beyond my knowledge. I don't know all about them. It's something I'm really interested in, though. I'd like to learn more about. But gyros are used in aircraft. They're used in,
Yeah.
Oh, they're used in what the heck is it? They used to mount a large gyroscopic instrument. I don't know the name of it. They would mount it like in an all-terrain vehicle and use it as they just drove, and I'm not sure of what the ultimate absolute accuracy of these things were, but they could literally navigate their way and plot their location while they were doing gravity surveys with gravimeters. So they kind of knew where they were. And they have to do a circuit. You got to start someplace, go out, map a certain area. These are instruments used in remote areas, and you'd have to make it back to where you started to determine the closure. But that's how they work.
Yeah, one of these days our iPad's going to have a sensitive enough gyro in it to sense the, the rotation. It's going to happen. 10 years. I'll give it 10 years.
Maybe sooner.
Maybe. Yeah, so I think the important thing to me, one of the things that really stood out to me, the thing that I learned when you came out here, I learned a lot when you came out here, actually. But the one thing that I learned that really kind of stood out to me was that GPS uses that Earth-centered, Earth-fixed coordinate system.
Right.
And I had never heard of that before. So whenever you said that, I was like, wow, that's really interesting, because in order to actually get an X, Y, and Z coordinate, you have to be working in 3D space.
That's right.
And to me, it becomes intuitive at that point to realize that, GPS cannot work on a flat plane, because that's what a lot of flat earthers like to say. Well, it's just longitude and latitude. It's just two coordinates, so it's a flat plane system.
Oh, yeah, they're leaving out they're leaving out the height, the altitude.
That's right.
It is a three-dimensional system. The mass center of the Earth is the origin of that reference frame, or that coordinate system. It's 0x, 0y, 0z meters. It's in meters. And as these satellites fall around the Earth in their orbit, those coordinates of those satellites can be computed at any instant in time. This whole thing depends on timing and being able to track those signals to intersect those ranges. So, like at some instant in time, that satellite has an XYZ coordinate.
Right.
And when you intersect 4, 5, or more of these satellite ranges to your position, you are going to compute your XYZ coordinate on Earth, which then can be converted to a latitude, longitude, and ellipsoid height.
And when you actually track 4 or 5, or 6 of these satellites with your professional equipment, like what type of accuracy are we talking about?
Good question. Also let's also bring up the fact that it's not only GPS. GPS is the United States. GLONASS is the Russian system. The European Space Agency has Galileo, and the Chinese have something called BeiDou. And there are others. I know the Indian and Japan have systems that I believe are, oh shoot, what's the word? Geostationary. I don't. I think they pretty much hover. Oh, anyway,
Yeah.
you get the idea. There's
Yeah.
more. There's a lot of different navigation satellite systems out there, and our equipment today track most all of those. So it's GPS, GLONASS, BeiDou,
Oh wow.
and Galileo, and they all contribute. Now, each one of those constellations of satellites are in different orbital planes at different altitudes, and maintained by those different agencies. But all of the parameters are published. It's, you can go and download the PDF manuals of all of the specifications on how these systems work. And so it's open source kind of, and the reason for that is so that all these different manufacturers can enter the market with their brand of device.
Yeah.
And try to be innovative about how to combine all of these different observables. And because accuracy is the name of the game, and that's where that was your question: how accurate can you get? Here's the thing: when you turn on one GPS receiver, even if it's the most expensive geodetic quality receiver that tracks all these constellations and multi-frequencies, L1, L2, L5, you name it, as a standalone unit, it's only going to be as good as your phone or your Garmin in your car. Okay.
Okay.
It's just going to give you what's called a pseudo range position. It's a navigation solution, and it it's a pretty good estimation of where you are on Earth, right?
Good enough for Google Maps.
Good enough for that. Good enough for that type of application. Now, it's good enough to go find that same fishing hole. Good enough to find your way out of the woods. It's
Right.
perfect for that. What we do in surveying is we use two receivers at a minimum. Okay, with two receivers, we are it's a technique called carrier phase differencing, and it's the exact same technique that has been being used for a long time in something called VLBI, very long baseline interferometry, where they have these they have these radio dishes pointed at quasars, like up in Yellowknife, Canada. There's where are all there are these observatories all around the world, and that's what they do to determine the difference in position between these observatories. It's called space geodesy, and it's used in astronomy and everything. And they can determine. They've been doing this since the 60s and the 70s. They literally track these carrier signals from quasars, and they difference them between the two stations, and they can come up with millimeter accuracy between those stations.
Whoa.
doing that technique. So
like two stations on the opposite sides of the planet, millimeter precision between those two.
Yes.
Wow.
And they do this. They've been doing this for many decades, and all of that is part of this whole thing called the International Earth Rotation Service. I love saying that. There is a thing called the International Earth Rotation Service, and all of these different space techniques are part of that daily solution. I mean, they determine the Earth's polar wobble. There's a lot going on that's computed every single day. The Earth tides. Not only do we have ocean tides, we have Earth tides. So the terrestrial part of the Earth fluctuates too.
Anyway, that's crazy. International Earth Rotation and Reference System Services.
Yes.
Wow.
Isn't it cool? It's cool stuff.
Does the Earth rotate? Let's ask these guys.
And so the other part that is part of that is satellite laser ranging, and lunar laser ranging. I think you and I were talking about that couple of weeks ago.
Yeah.
So all of this stuff enters into these solutions that they do every day, including the IGS, which is the International GNSS Service, which are all of these receivers mounted on pedestals, substantial structures mounted in bedrock, and you name it. They're very solid locations that track all of these navigation systems, GPS, GLONASS, and all the rest of it.
You know, whenever
Every day, and it's like thousands of these receivers are all tracking this information, sending it to these processing centers to compute all those coordinates.
So I was going to tell you this is that you told me that whenever you were here in December.
Mm-hmm.
And so it's kind of one of those things like you buy a car and then all of a sudden you see like that same car everywhere on the interstate, you know?
Right.
Like you mentioned that. And then all of a sudden I started seeing these things. And I saw some, I swear, like mounted on some of the taller buildings in New York. Was I seeing the correct thing? Was
I don't know
seeing what I thought I was seeing?
I don't know what kind. I mean, you'd have to see what the shape of them were, but they could have just been cellular antennas. But you'll also see a little antenna, a little GPS antenna mounted at these.
It definitely looked like your antennas. Like it had that same rounded thing. It looked like your thing. I don't know.
Well, I was going to say that the small ones that are about the size of your fist are really not for positioning, but for time transfer. And you'll see those at the there'll be that fenced in area at a cell tower location. Yeah. There's a little hut there. You'll see little teeny GPS antennas on those, and those are just for timing. They're just trying to get the time transfer aspect of GPS using the precise timing.
So that's just to keep their clock straight.
That's right.
That's very interesting.
Keep all that synchronized. But But for the surveying that we do, you have to have two receivers, and what you're interested in is the vector from one to the other, and that is the dx, dy, dz from what you might call your base point to where you are. And in survey terminology, we call that you're operating a rover because you're roving around. And the base unit is usually set up on a known control point. I mean, that's how we did it in the old days, was to set up your base unit on a survey disk or some other, known point, and then you would determine your position. All the unknown positions you would go to and determine it from the known position. But now, for the past 10 years at least, we literally get that information right off the internet because these base units are, mounted on buildings or other structures, and they're all feeding their data onto the internet. So if I have an internet connection, I can get instantaneous positioning at centimeter level, like really good three-dimensional positioning.
Yeah.
Almost instantaneously. It's like it works very quickly. Now, when we did Little Tinsis Bayou, we set up a base unit up on the shore when we were using the boat and going out trying to measure the distances between the lights.
Right.
I guess we got about halfway across, and I ran out of radio range. So, but
I was actually thinking about that after the fact. Is that I have some police officer friends, and I think that they could actually access that crossover in the middle.
Oh.
And you could actually set up your base right there, like up on top.
Well, if I could get access out there, I wouldn't do the GPS. I'd take the theodolite out there. You know what I mean?
Yeah.
I mean, GPS is easy. Getting the theodolite out there and visual, getting a good visual, that would be cool.
Absolutely.
If we can get permission to do that, I'll bring the T2.
Okay, I'll make some calls and see what I can do.
That would be worth doing because we could do a 360 looking around, and isn't it the fact that you can't see the land from there? I mean,
from the center, you'll be able to see the land.
Oh, you can. Okay.
Yeah, you'll be able to see it. It's only 3.5 miles, I think, to the center. So from up there, the elevated position, you'll be able to see it.
Where are we talking about?
I was talking about Little Tensas Bayou.
Oh, I was thinking the Causeway.
But the Causeway, yeah, if in the center of the Causeway, you cannot see the shores of each side. You can see the tall buildings in New Orleans. You can
That's yeah. If you can arrange that, T2 is coming.
Okay. Let me see what I can do. I'm not sure if I can or not, but I'll try.
All right.
I just wanted to tell you this little anecdote.
Yeah.
I typed International Earth Rotation and Reference System Service into Google, and the first video that pops up is yours from 2016.
Which video popped up? The GPS antenna one?
It's named in your video from 2016, September 25th, 2016 is named International Earth Rotation and Reference Systems Service.
Oh, maybe I mirrored it or something just for the fun of it.
Probably.
Yeah.
It's interesting that your video is the first one, though, isn't it?
I don't remember putting that up there. Anyway. I must be part of it.
Yeah, you're part of the conspiracy, man.
Yeah.
Or we all are. Well, Jesse, I really appreciate you coming and doing this, and I'm glad you're going to be coming back out in January, man. I think we'll have, I think we'll actually have a little less of a stressful time because the last time was fun, but it was a little stressful hanging those lanterns. But this time we won't have to be worrying about any lanterns. We'll just be able to focus on the Causeway, and I think it's going to be a lot of fun. Just gotta pray we get some good weather, man.
Yeah, I really hope so. In fact, I was looking on time and date, just looking at historical, just to see what it's like in January. But we'll do what we can do. Well, one thing's for sure, if we can triangulate the room window.
Right.
We can do that in any weather. I don't care about getting wet out there. So we'll get that done, right? And even in bad weather, I can still do a thorough. I want to saturate the bridge, the Causeway. I want to do the northbound and southbound lanes at like 1 second intervals instead of 15 seconds. Drive nice and slow.
Yeah, that would be amazing.
Nice and slow. Put the receiver up on top of the car instead of on the front. That way it won't have any obstruction. Oh, I forgot to tell people earlier, I did an actual level survey to determine the antenna height above the street. So we'll do that. Make sure that we know, to the nearest 1/8 inch, basically.
Yeah.
Where's the antenna in reference to the roadway? And that way you're actually surveying the road, not the top of the car.
I'm definitely interested in those GPS coordinates you already have, and I definitely want to go back and repeat it and see where the anomalies might have been, or where maybe there is an extra foot of height in a certain area. That would be very interesting to have, because I think we could communicate that information to Walter, and he'd be able to update his model.
Or really verify. I mean, you think about this, Sally. All of the photographs you've taken, people want to say, "Oh, it's trick photography. Oh, you did this. You did, anything except it's a picture."
Right. Exactly.
So,
I try and use reason with them and say, "Look, Jesse Kozlowski was there. Okay, he was there witnessing me do this. He watched it happen. There's no trick to it. It's just a photograph, man." Yeah.
Take this camera, hook it up to that telescope, take the pictures.
Exactly.
But now we have, and like you said, when we do this the next time with a dense saturation of once per second, or I can even do it at 5 hertz, drive 35 miles an hour, 5 shots per second, we'll have a profile that goes up the humps,
Right.
It won't be just a shot here and there. It'll be like a real profile line,
right,
up and over. Yeah.
Yeah, that would be awesome, man.
That's going to be awesome. And then, we can do that in any weather.
Yep.
But if we have good weather, you'll get some good new photographs too of the Causeway.
Yeah, we're going to have good weather. I mean, from that height, it would have to be just storming the entire time to not
Right.
get
Right.
any photographs. So, I mean, definitely going to end up with some good photographs. And it's not necessarily a bad thing to have some cloud cover. Kind of keeps the sun off the water.
Yeah.
Gets rid of any type of mirages that could be happening whenever the sun's off the water. So,
well, hopefully everybody now understands there is no clown frown. And this whole thing about your photograph, they keep looking on the left side of the causeway going, see that there? You know, the part that you had indicated is definitely a reflection, but
yeah.
they're all trying to see, that's not curved. Yeah. You're right. It's not. You can't. No kidding.
Congratulations, you have validated the globe.
Yes.
that's what we predict, right?
Exactly.
Goodness gracious.
All right, now we're up at 2 hours, and that's probably it for tonight.
All right. Yep.
Thanks so much for coming on my channel, Stanley, and this has been fun.
Absolutely, Jesse. Anytime.
And thanks for everyone to hang out. We have like 23 viewers here. That's a lot for my channel. So thanks everyone for tuning in, and we'll see you all next time.
Thanks, Jesse.
Thanks, Stanley. All right, bye-bye.